going.
Hi, this is Zach, Drew, and Dean, and we're presenting our WazeApp project.
Okay. So the problem statement here we have with our WazeApp project is this project is an interactive web application implemented in JavaScript and HTML on the front end with a Java backend, connecting through Ajax and Spark Java API. The front end utilizes the Google Maps API for displaying the 20,000 plus nodes of the California road network intersections and 20 plus thousand connected edges on an interactive map in your favorite browser. The application has two major key operations. Calculate the three shortest distances between two selected intersecting nodes. The map will highlight the edges of these three paths as well as display the distance associated with each respectively. 2. Highlight all adjacent nodes to a single node when that node is clicked. We also added additional functionality on hover over and on click. On hover over, the node is identified with the ID number from the dataset used to populate the markers. On click, the map displays the box that includes the latitude and longitude of the marker. Now we're going to talk a little bit about the building complexity of our data structures. So for the shortest distance calculation, the initial data is processed on the back end into node and edge structures to embody a prototypical undirected graph. Our naive implementation is based on the use of Dijkstra's algorithm for future queries, which is safe as we know that none of the edges will ever be negative. We also utilize a priority queue mechanism structure for efficiently dealing with our implementation of Yen's algorithm for the k shortest path calculation. We are not using the 1970s implementation, but instead we use an open source code based on the following recent papers by Martins and Pascal that builds off Epstein's and Yen's papers. The building complexity of the completely parsing through the text files and creating the actual structs utilized by the Java backend is big O of V plus E, vertices plus edges. And then for the highlighting adjacent edges, we initially had a script parsing the text file into a JSON format for the JavaScript front end to easily process at runtime in constant time. The complexity for this pre-processing step was O of E, since we were going through the edge text file linearly and parsing it into a JSON. When we got further into our final implementation, we still had a build time of E, and we are still using a graph struct as a set, which is comparable to the adjacency list from an array. So the building complexity of our adjacent edges is E.
Okay, so in terms of our query complexity analysis, when you actually want to go out and visit these data structures and pull the information for the two major tasks for our project, we have the shortest distance calculation, which again utilizes that algorithm we spoke about earlier based on Yen's algorithm, but it's slightly optimized with the last 40 years that people have been working on it. So we found some nice open source code, and there's a couple good academic papers that we'll link with our project. Those papers will demonstrate more formal proofs that the runtime will be k of n, so it's for k shortest paths. We limited it to 3 shortest paths as that's the goal, and it's so it ends up being the 3 dropping off and being n times m plus n log n, as you see here. In terms of queries relating to finding the adjacency, we actually got it down to constant because we pre-process all of the neighbors for each of the nodes. So when it first loads up into our data struct, we have the building complexity, but again, since the average node only has 1 or 2 neighbors, it's down to constant time. Worst case, if you're thinking about theoretically on a map where one of the nodes can have every other node on the map be its neighbor, in order to draw the lines, it'd have to have a complexity of V, because it'd have to go and draw a path to each possible node, each possible neighbor.
So now we are going to demo our WazeApp. As you can see, there are a bunch of nodes populated on the map. You can click on any node and it'll give you a path to the adjacent nodes, highlighted by the red line. It gives you the latitude and longitude for each marker as well. To calculate the distance, you click the distance button,
Let's zoom out a bit.
and you can click any two nodes.
Too far. Let's go here.
And you are able to see the shortest path, the second shortest path, and the third shortest path. The shortest path is highlighted in the red, the second shortest path is highlighted in the blue, and the third shortest path is highlighted in purple. You can see the distances of each path as well, shown in the info box.
So let's try do it again on a wider set. So I click the distance, and now you select the source, and you select the destination. And you can see the red path is going to be the shortest with 1.39, then slightly longer is this blue path that goes up here, and then third is a purple path, which you can kind of see, and if you zoom in you can get a better detail of where the paths are going. Okay. And what we learned is a lot about Yen's algorithm. We read a couple academic papers on the optimization. So one of the major kind of milestones and obstacles we came into, our initial implementation was Dijkstra's, which is simple, but we were trying to find unique paths from a source to a destination, and by removing the edges along the initial path. But obviously that didn't work very well when the source and destination nodes typically only had two edges coming out of them, because once you removed one of the possibilities, you weren't able to reuse any of the edges before, so you were only finding usually two paths at the most. So obviously here we have it using some of the previous nodes and previous path, and just finding the shortest supplemental, unless the second shortest is a completely different path altogether. And that's about it.